I will be talking about experiments with where we use ultra-cold atoms to build really complex and really rich many-body, like artificial many-body quantum systems, and where we can really study them on a single particle, single atom level. And it's actually quite exciting because it really gives us a great view into this otherwise very hidden quantum world. And so it's about quantum mechanics. I will try to really explain things from ground up fairly intuitively. Let me know if there are questions, but yeah, let's get started. So we use ultra-cold atoms. Let's start with that. What does that mean, ultra-cold atoms? So we are really cold. This is a logarithmic energy scale here. Sorry, I use this one here. So here you have room temperature, right? So this is about at 300 Kelvin, right? And if you get colder and colder, you get closer and closer to absolute zero temperature. This is a logarithmic scale. In our experiments, they're about, if you have liquid helium or so, you're a little bit colder than room temperature on this scale. But if you go 12 or 13 orders of magnitude colder in temperature, extremely close to absolute zero, that's where these experiments are. Another comparison, by the way, is if you had a thermometer reaching from here to the moon, where the room temperature reading is at the moon, then we would only be the width of a hair away from absolute zero temperature. So extremely cold, also colder than the hottest man-made temperatures. Like the Large Hadron Collider energies are over there. Okay, how do we get our atoms cold? Ironically, we use laser beams to cool them down. Normally, you would expect that laser beams heat up things, but if you have a gas of atoms, you can tune the laser just right that if the atom flies towards the laser, it scatters photons, and the photon recoil, like the photons, slow the atom down, essentially. Here you see such a cloud of cold atoms that are trapped by laser beams and cooled by laser beams, and you see how slowly it flies apart. Right? At room temperature, atoms fly with about the speed of sound. Here, we have cooled them, in this case, to the micro-Kelvin temperature, not that cold yet. And you see they have already slowed down quite a bit. And we see them because we scatter this, the laser light fluoresces, and we see the cloud floating inside a vacuum chamber. Right? Everything has to be in vacuum, really well insulated. Good, that gets us to micro-Kelvin, like a millionth of a degree above absolute zero temperature, but that's by far not enough. We need to get much colder, and so what we do afterwards is that we constantly remove the hottest atoms. I mean the atoms with the most energy, we constantly remove those, and so that means the rest gets colder and colder until we get for example, these are bosonic atoms, a so-called Bose-Einstein condensate. So you can see they slow down more and more. Good. But why do we do that, right? Wouldn't you think that, I mean, if you cool it so much, wouldn't just everything be at standstill and nothing happens anymore? It's quite the opposite. So what happens is that the quantum world is really, like quantum mechanics takes over. And at those cold temperatures, the gas of atoms behaves completely quantum mechanical. And what that means, I want to spend the first half of my talk on, essentially, to show you that. So the essence of quantum mechanics is that matter behaves wave-like. That matter is described by a quantum mechanical matter wave. Let's remind ourselves, so what does that mean? What kind of waves do we know, right? There are waves in water, acoustic waves, sound waves, radio waves, at low frequency radio waves, or at higher frequency electromagnetic waves are light. Here I'm talking about a slightly different wave, namely the de Broglie wave, matter wave. Waves whose amplitude tell you about the probability to find a particle at a certain location. And particles can be delocalized wave-like. Essentially, the particle, you have to think of a particle being at many places at once, and where it is described by this matter wave. That sounds a bit exotic, except you've all heard about such matter waves quite a bit, probably. If you think in chemistry, right? Orbitals, what are orbitals? Orbitals are matter waves that tell you where the electron may be. or the electron is really quantum mechanically delocalized around the nucleus, right? And the matter waves describing the electron tells you how this atom is delocalized, and the amplitude of the matter wave, the square of that, gives you the probability to find an electron at a certain position, right? But it's really, electrons around an atom are really kind of, you can think of them as smeared out around the atom, delocalized. Once you try to measure where it is, then you will always find it at one position. But before you're able to tell where it is quantum mechanically delocalized. And in every material, right, the electrons are widely quantum mechanically delocalized. They're really spread out over fairly large distances, actually, quantum mechanically delocalized, right? Oftentimes that, right, and that leads to a lot of important properties. Why do we have insulators and metals, right? This is all because of the electron gas in the material being delocalized. In this case, oftentimes you can simplify things and come up with very hand-waving kind of classical models of metal and insulator and things like that. But the underlying physics there is really electrons being quantum mechanical waves inside the material. The most interesting materials, like strongly correlated quantum materials, this quantum mechanical nature of the atoms becomes really important, and you really have very complex, strongly correlated states in kind of materials like high temperature superconductors or so. This gets really complex. Okay, so electrons, or like orbitals, these are matter waves of electrons. But why do we cool our atoms so much? I mean, even at room temperature, right, your orbitals are pretty good matter waves of electrons. Well, we want not matter waves of electrons, we want matter waves of the atoms themselves. So the position of the actual atom is now given by a matter wave. And so how does this behave? Like at high temperatures, you have a classical gas, the atoms move about with the speed of sound. And then as you cool down, the speed of the atoms becomes slower and slower, but that means the wavelength becomes larger, or in other words, the slower you are, the better you know the velocity of the atoms. And then Heisenberg uncertainty tells you that the position of the atoms need to become more and more quantum mechanically uncertain. And ultimately, when you're cold enough, kind of each atom you can think of as a little wave packet flying around. And once they start to overlap, then you get a so-called quantum degenerate gas. Then you get into the regime where things happen like a Bose-Einstein condensate, a Fermi sea. So this is where really the many-body quantum magic happens once particles are delocalized as a wave, and then these waves overlap. Because then the particles, even they lose their individuality. They become fundamentally quantum mechanically indistinguishable. And so we will see that in some examples. Make sense? Any questions? Good. And once we have waves, why is that so different from what we know from the classical world? I would say the most important property of waves is interference, right? If you have two waves that add up, you get a stronger wave. But if you have two waves that are opposite in phase, right, and you add them up in every point, you find that the result is 0. So two waves, if they're opposite and you put them together, they cancel. And this means matter plus matter can be more matter, or sorry, a matter wave plus matter wave, or one matter wave plus another matter wave can be less matter. So this interference is really what makes quantum mechanics, the wave nature of atoms so special, essentially. Interference you have probably seen with light or so. You know, if you have soap bubbles and you see the different colors reflecting, that's actually caused by interference of light at the surface, or if you have an oil film, the colors. Well, anyway, so in our case, it's the actual matter waves that interfere. Good, so we have cold atoms. They're cold enough to be in this quantum regime where they really lose their individuality and where they behave completely matter wave-like, and where these matter waves overlap and we get a quantum degenerate gas. That's our starting point. In our experiments, what we then do is we fill these atoms into a so-called optical lattice. So this is a potential landscape, kind of like an egg crate, an egg carton, where the atoms sit inside and move inside. And let me actually show you a video that my PhD advisor, Ted Hensch, took a long time ago that shows you how it can be that we can trap atoms in light. So light can have mechanical forces, very tiny usually. The only example in nature I can think of is like a comet tail, where photons kind of accelerate the dust particles away from a comet. But here, if you have a lot of light, like in a laser, and very small particles, then you can get sizable forces. So here, these plastic beads are trapped in light. And you may know that from biology, like in optical tweezers or so. With a focused laser beam, you can trap a particle and move it around. And here you see an example, little plastic beads swimming in water, and they are being trapped by these laser beams. They always go to where the light is brightest, right? Our atoms do the same thing. So we can trap the atoms in these optical lattices, where they go to where the light is brightest, and that forms a potential landscape. With that, we can do a lot of fun things that I will tell you about, but we can do one other thing. What we developed is quantum gas microscopy, where we can image all the individual atoms in the optical lattice. Essentially, we can make suddenly the lattice extremely deep, hold on to the atoms very tightly, do additional laser cooling, and scatter photons. And so each atom fluoresces some light, and that we can collect on a camera. And then we get pictures. So here's a sketch of a quantum gas microscope. This is how it looks inside. So there is a very high, this is a vacuum chamber and a lens inside and a high resolution objective on top. The whole experiment is a bit more complicated. Looks more like that. But in the end, we get pictures like this. And if you look closely, you see that these dots here are arranged on a regular grid. These are atoms in the optical lattice, right? So each dot here is exactly one atom that is trapped in this optical lattice, which you can think of like an egg crate kind of a potential landscape where you have the individual atoms sit. Okay. So this is nice, but the coolest thing about this is before we take this picture, each of these atoms is everywhere. This is a Bose-Einstein condensate in the lattice, right? And if you write down the quantum mechanical wave function, you literally write down atom number 1 is everywhere times atom number 2 is everywhere. So all the atoms are everywhere, essentially. And only as we start illuminating the sample and starting to collect photons, we slowly get information about where the atoms are, and then the wave function collapses, and we find one particular realization. For example, it looks just random, right? But quantum mechanically, before we took the image, all the particles were really delocalized over many lattice sites. Okay. We can also take even movies, how the particles move, but of course here we're constantly observing them, right? So here they're not delocalized, here they just move like classical particles. So that's why normally we only take one picture in the end after preparing a state to analyze it. Yeah, and then we can use those atoms to build all kind of interesting quantum systems. But, and so essentially we use these atoms like as Lego bricks to build all kind of different quantum models that are highly relevant, you know, if you want to understand quantum materials in material research or, yeah, I will get to that. But let me first tell you a little bit more about how these atoms are now essentially our Lego bricks from which we can build these artificial quantum systems, many-body quantum systems. Let's start with a single brick, a single atom, okay? How does an atom now move in this optical lattice, in this potential landscape that we form by light, right? Classically, it couldn't move at all if it is at rest here, or if it is in the lowest possible energy state. You would have to heat it up for it to hop over the well. But quantum mechanically, the atom can tunnel through the lattice site. Like it can go through this forbidden region briefly, essentially, and so it can tunnel from side to side, just like an electron can tunnel from one atom to a different one, or within an atom from different sides. In a molecule between different atoms, like in graphene or so, if the valence electrons are delocalized. Okay, so the atom can tunnel between these sites. And so what happens if you just put one atom there and let it tunnel, right? What would happen classically? So classically, this sounds a lot like a Galton board, right? If you just have this kind of this nail board where at every point the particle can make a 50-50 decision to go left and right. If you let it go here, and this is kind of the same as many tunneling steps, classically you would get a Gaussian distribution here. You have all kind of different paths that that the atom could go classically, or that the particle can go classically. What is now special about the atom quantum mechanically tunneling in this lattice? The cool thing is that it then really spreads like it essentially takes all of these paths at the same time, right? It knows about all possible paths. It, as a wave, travels through that potential landscape. And this is equivalent to saying the particle is really in a superposition of all these different ways it could go, right? So it travels all of these paths at the same time, and then you have to add up all of these paths. If you want to know where the particle is in the end, you have to add up all of these different paths. But you can have interference. Some paths will cancel out. In fact, most of the ones in the middle will actually cancel out. But the extremal ones here, they will add constructively. And so that will completely change the problem. So this is called a quantum walk. Let's try that with the atoms. Let's put an atom on a side. This corresponds to a little wave packet that is located on this side. And if I then turn on the tunneling, this wave packet, this matter wave, will spread out in the optical lattice. And remember, the matter wave tells me the probability to find a particle somewhere. So if so at this time, I have to assume the particle is really in a quantum mechanical superposition of all these possible locations. But if I then measure, if I shine light onto it, then the wave function will collapse, and I will find the particle at one particular point here. But the probability to find it here is proportional to the square of the amplitude of the wave function. So what that means is I can repeat the experiment over and over again, and then I can see how many atoms I find at different locations. And in particular, there are also, for example, some sites where you have destructive interference. Here you will never find a particle. And if I repeat the experiment over and over again, I prepare the system, I let the atoms tunnel unobserved, and then I take one snapshot and I record where the atoms end up. then I get a pattern that reflects the shape of this wave function. So I can measure that by just repeating the experiment over and over, sampling, and looking where I find the atoms. This way I can map out the single particle wave function. And so let's do that. Here's in the experiment, this is the actual picture of a row of atoms that we have prepared. And now we don't let them move vertically, but we now turn on tunneling horizontally and let these atoms tunnel horizontally. And so if you do that over and over, so this is not a movie of a single atom. Each time it's a new, fresh kind of a set of atoms that always starts in the middle and then moves for a certain amount of time. And we see that the longer we wait, the further out the atoms come to lie, but this really maps the probability of the wave function. And if I do the statistics of that and measure that, then I see, so this is position versus time, I see that the wave function spreads out like this. And in particular, the atoms move ballistically here. Just the position is just proportional to the time, which is exactly what you would calculate, but which is very, very different from what you get in a classical diffusion. Right? Essentially, it goes all these different paths simultaneously, but only these very extremal paths here interfere constructively, and that's why you get this ballistic motion in contrast to a classical diffusion, if you have the atoms coherently tunnel in the lattice. Yeah, but here you can see that, and the pattern already tells us we have a very coherent quantum system. If you put the atoms there, they behave super coherently. We have another, a bit more direct way to show that, and this is if you tilt the lattice, then they don't keep spreading out. They actually, if you do the math, you actually find they do so-called Bloch oscillations. They would come back to the original site. And that really classically you can't conceptualize. If you let them go, right, classically, it wouldn't know where it came from. It would just diffuse around and would never come back. But quantum mechanically, it should be able to perfectly come back if everything's perfect. If there's any decoherence, or if there's any way to tell where the atom is now, then the wave function would collapse and would be here and would not come back anymore. So let's try it out in the experiment. We position the atoms here, then they spread out. But after longer times, they in fact come back perfectly. And that directly shows us how coherent the system is, right? It's completely, it's a very well unobserved quantum system. And the fact that they come back so nicely directly shows us this amount of coherence that the quantum system has. Yeah, I think there's a picture of these quantum walks here. Good. So this is one puzzle stone, or one Lego brick, essentially. Let's build something more. Well, the first thing you have to consider is two together. So how does that work quantum mechanically? If you have two particles now, right, they can both tunnel. Now, what does become important now is the so-called quantum statistics. It's a fairly subtle but really important thing. There are differences between particles. So these atoms are indistinguishable fundamentally, and that means if they move, you always have to consider. They are bosonic and fermionic particles, and they behave different. If you exchange the two particles, in one case you have a minus sign in your wave function, and in the other case you don't, and that makes all the difference between the difference between electrons, which are fermions, and photons, which are bosons. And so we'll see that will play a role. Also, they can interact. If you have two atoms on the same side, they can repel each other. And that causes the on-site interaction energy U here. So let's try the following experiment. Let's put two atoms on two neighboring sites and then let them tunnel. And let's ask, how likely is it that they end up close to each other after some time or far away from each other? So now you have to consider two paths, essentially, that the atoms can take. If you measure two atoms here, you don't know which one is which because they're fundamentally indistinguishable. And this means they can either have taken the red path here or the green path where they cross. But if you count the number of steps that both of these paths have in total, you find that it's the same number of steps. And this actually means that for bosons, these two paths interfere constructively. So this is quite likely because these two paths, the waves corresponding to the green and the red path interfere constructively. So it's quite likely to find the atoms next to each other. As opposed to in this case, here you can see the green path is 2 steps longer in total. Like each of them is 1 step longer if you go across the middle line. The green path is 2 steps longer. With each tunneling, the many-body wave function changes by 90 degrees. So 2 times 90 degrees is 180 degrees. So now they're opposite in phase, and they cancel out. One wave plus opposite wave cancels. And so this would be quite unlikely to find them on opposite sides with bosons. Yeah, and that's what we find. They are, in fact, in the experiment, if you do that, they tend to be close to each other. If you use fermions, then you get the opposite, because for fermions, if you exchange them, you get a minus sign in the wave function. And with that additional minus sign, this turns into destructive interference, and this turns into constructive interference. So just by changing from fermions to bosons, you find now it's quite likely to find the particles on opposite sides. This is kind of the easiest setting where you can see the difference between bosons and fermions. And the funny thing is actually what determines if an atom is a boson or fermion. It's the total number of constituents. So like different isotopes, depending on how many neutrons they have, could be boson or fermion. So they behave completely different at these cold temperatures, as opposed to at room temperature where you can hardly distinguish different isotopes. But here, 2 different isotopes would behave completely different in terms of quantum statistics. Okay, so that's the second important, and then we can do quantitative correlation measurements of these positions, and then you actually see that, yeah, it looks really exactly like what you would calculate for the bosonic and the fermionic cases. Good, so with so much quantum weirdness, you can imagine if I now have many of these particles, then it gets really interesting, right? Then you get very complex situations, very complex physics. Because just think about that. I just showed you how each particle is delocalized over large areas, which means each particle is everywhere. But then the particles also strongly feel each other. They can interact with one another, right? And which means that every particle depends on every other particle. So every particle is everywhere, but also sees all the other particles, which likewise are also everywhere. And so you can see how that gives rise to a huge complexity. And this is this complexity is actually what the Institute of Quantum, what is it called? CCQ is all about, is all about, right? Because you find this in nature in different, like in material science, right? If you want to understand materials, things like high temperature superconductors are still not really understood. Why? Because you have this kind of many-body quantum mechanics going on. And it turns out it's incredibly hard to compute that. They're making great progress and are maybe world like leader in many aspects of this. But it's really but they will tell you it's really hard to compute that, because just imagine every particle being everywhere and also seeing the other ones, right? Sometimes you can simplify things a bit to some kind of mean field, but it is fundamentally hard to Good, but the great thing is we can just build it in the lab and study it and try it out and build it in this clean, coherent way where we can even probe it on a single particle level. Where we can take a snapshot, right? I showed you how we can take a snapshot, take a picture. Just imagine being able to do this in a real material. Like you stop time and you measure the position of every single electron in your quantum material, right? That's the corresponding thing we can do in the lab. And so the idea is then that our atoms in this optical lattice, they can essentially help us to understand some of these models and be a model system for what electrons do in an actual crystal lattice in an ion, right? If you have a quantum material here, you have the electron gas moving in this ion crystal, and that gives rise to all the interesting physics. And we have this model system with atoms in an optical lattice instead. Like, for example, material science, condensed matter, there are lots of applications for these kind of ideas and lots of materials that you would like to understand better. How can I understand it theoretically? Well, typically these real materials are way too complex. You have to start with a simpler model. But even then, these simple models are really computationally difficult. And the nice thing is that we can kind of build these simpler models, and then we also have a more direct comparison to the computations. Just as a little examples, kind of like, why is this hard? If you have, for example, 300 spins, the full quantum mechanical state of 300 quantum spins, and they're all in a superposition of all the different possibilities. Even just to write down that quantum state would take more memory than the size of the would take more memory than there are atoms in the universe. So because it scales the so-called Hilbert space, so that it becomes exponentially large. Good, but our cold atoms we can now use. Right, so could we just use a quantum computer? And what is that anyways, right? So the idea of a quantum computer is essentially that you have a very controlled quantum system. And as you know, like full-blown real quantum computers are quite difficult and still a way out. But Richard Feynman had the visionary idea that you could even say, even led towards quantum computing and so on, that if you want to understand a quantum system, you can maybe build a model system and study that instead. And so this idea is is called quantum simulation. And so the idea essentially is, if you can't do like a digital simulation of it, can you build like an analog computer essentially? Sorry, I built on this Lego theme here. So the idea is that you have kind of like an analog computer. You build an analog system, you build a quantum system to understand a different one that is not as accessible. And there are examples in history for like classical analog computers, right? Like before you were able to build a digital computer that can calculate complicated things, or like a trajectory of something, or so. They built fairly elaborate classical analog computers, electronics, for example. The idea is to do this now with quantum systems. If you have a quantum system that we can't compute, can we build kind of an experimental analog of that quantum system to understand it better? So one example is they started in 2002 with the superfluid to Mott insulator, where we were able to, for the first time, to create a quantum simulation, essentially, like to build a well-controlled quantum system, like a strongly correlated quantum system that was useful to understand a model that came from a different field of research. And so there has been a lot of work since then, and I want to show you some work on a so-called Fermi-Hubbard model, which is closely related to actual materials. So the Fermi-Hubbard model is just what I told you earlier. Atoms tunnel in a lattice side. If you have two atoms on the same side, they repel each other. There's one additional ingredient. You have two spin states here, spin up and spin down. So just like an electron can be spin up and spin down. This is denoted by the two colors. And these atoms are fermionic. And with fermionic atoms, you can only have one atom per spin state on the lattice side in the lowest band. So this is conceptually very simple. You just have this tunneling described by this, and the on-site interaction described by this. Looks really simple, right? The funny thing is that until today, it's not really understood even what the phase diagram exactly looks like. And there is a lot of research here also to determine, for example, is there like or under what conditions has a model like that, for example, a D-wave superconducting, D-wave superfluid phase here. This is the phase diagram, but it's actually, or this is what the phase diagram is believed to be, but it's actually partly inferred by what is known from high temperature superconductivity, because this is kind of a toy model that may explain high temperature superconductors. And it is believed that this model probably already has phases like this pseudo-gap phase and strange metal phase and so on. But from these names, you can actually tell that these things really aren't particularly well understood, what that really means on a microscopic level. There has been a lot of work with cold atoms, starting with these experiments, and then these quantum gas microscope experiments. But it's a challenge. We have to get cold enough to get to these interesting states. And so the current state of the art here is, the kind of states that you get there is like an anti-ferromagnetic state. You get the spin ordering, which we saw appear. And so this is essentially that if you get cold enough, the atoms form an anti-ferromagnetic state, because the atoms on neighboring lattice side want to be in opposite spin states. So this would be on this line of the phase diagram, you get into this anti-ferromagnetic phase. But then the interesting and really complex physics happens if you now dope the system, meaning you have additional particles or additional holes, because in a real material, this would correspond to charge transfer, like electricity, conductivity, and then ultimately superconductivity. The physics there is really quite rich. So if you have one-dimensional lattices, like you can see here, we can actually do a very similar experiment to what I showed you earlier with the quantum walk. But here now, I have each lattice side filled with an atom in this Fermi-Hubbard model. There are also two spin states, which I don't show here. But then I keep one lattice side empty. We call this a hole. And if this hole moves, this is kind of like electricity transport in a material. So let's prepare this row of holes here, and then we can again turn off the potential that keeps the holes in place, and we can look how the holes move left or right. And if you do this experiment, we actually find we get exactly the same quantum walk I showed you earlier for single particles. But now it's not a single particle, now it's a hole in a Fermi-Hubbard model. Why is it just the simple Hubbard model? Wouldn't you expect something more interesting to happen? Well, it's actually in a 1D Fermi-Hubbard model. It's actually very elegant. It's very simple. A spin and charge completely separate, like you have spin-charge separation, and the holes just move independent of the magnet. Which is kind of intuitive if you think about it. They just move this dislocation in the magnet over. And in fact, there were very nice studies to show that. But it gets much more complex once you have a two-dimensional system. So one way to understand this is this kind of toy model where you start with just like a classical Néel state. In reality, the antiferromagnetic state we have is really a quantum magnet. It's much more complex. It's SU2 symmetric. The spin symmetry is not broken, and there are a lot of local quantum corrections and so on. But as a rough model, you can think about it like a Néel state, just like a checkerboard shape of spins up and down. And if we assume this simplified picture, and we have one hole here, so one missing atom, how would this hole now move? if the hole moves in this direction, you see that it creates a lot of unhappy bonds here. The spins on neighboring sides want to be opposite. And so essentially, if you move the hole from here to here, it creates a lot of unhappy bonds. Let's call this a string. And so this now has to behave very different from the normal quantum walk, because now this path here is essentially entangled with the spin state. By looking at the spins, you can actually figure out which path the hole took. And so then these different paths, for example, couldn't interfere anymore in the same way they did. It could also be, so there are recent ideas that you can take this idea a bit more serious and really think about some effective model where you have these kind of strings which are actually, which link a spinon, like a spin excitation, and this hole excitation. And this hole would actually delocalize around the spinon and form a polaron. It's kind of like a hyperactive dog on a leash, except it's really, the hole would be quantum mechanically delocalized around this spin. And then maybe there's some interesting dynamics. This is a bit related to what you calculate in high energy physics. These strings could break, and then you have a magnon, and so on. Anyway, this is a model. These are new ideas. You can't really calculate if this picture is good at all or not. But we can experimentally try to see if this is maybe a good picture for this doped Hubbard model. And if this maybe brings us closer to understanding how, for example, high-temperature superconductors work. So we went out to try that. We took snapshots of such a doped Fermi-Hubbard model, and then we do statistical analysis to try to compare the pictures we get of the atoms. Right? These strings become visible in the pictures if we measure the spin and the charge, and we can analyze that and see if our experiment agrees with a picture like that. But of course, we can also agree, we can compare it to all kind of other theories. And so we have done quite a bit of work there. Also, for example, what becomes really helpful here could be, can be machine learning. We may not even know what we want to look for here, but if you just, if you use machine learning to see if a machine learning algorithm can associate a simulated pattern with what we see, then we can also try to find out what theories are describing the situation best here. Because if you think about it, there are really lots of high-order correlation functions that play a role here if you have this kind of physics like a string. Anyway, to make a long story short, we have some evidence that these strings seem to be, that the experimental data is consistent with such a string picture. And we looked at different theories, and some fit better than others. So we are really starting to explore that experimentally in regimes where it's extremely hard or impossible to calculate these things. What's even harder to compute is dynamics. But this, of course, for us is quite natural. We can do the same again. Here's a 2D Hubbard model where we have one hole in the middle, and then we let the hole move. And as I said, this hole, if this hole is dressed by this kind of magnetic cloud in a polaron, then it would move in a certain way, and we can probe that. And so we did that. This is how the hole moves away at short times. You see at short times it moves again just like quantum walk, but then quickly it varies from what you would expect from a quantum walk. But how does it move over longer distances? Again, at short times it moves just like a quantum walk, but then it slows down quite a bit. And importantly, we found that the whole motion is just, so the difference between the blue and the green here is that we change the magnetic energy, like the energy scale of the magnetism in the system, and we see that the whole motion is now, for short distances, it's just given by how quickly it tunnels. For long distances, the speed of the whole motion is given by the magnetic interaction. So that really indicates that we have a polaron here, and we can measure the nature of the polaron. We're currently we're currently upgrading the experiment to further lower the temperatures to really get into these interesting regimes where you would expect D-wave superfluidity or so. And then we really also want to, what's nice is that we can really probe it bottom up then. If we don't just have a single hole, but how about we have two holes in there and study how they move, right? Would the holes move independently, or would they maybe move together in some correlated fashion? If they do, that may be a D-wave Cooper pair. That may be the same kind of thing that happens in a high-temperature superconductor. And so we could try to figure that out and then have more holes and have them boson-condense essentially in into a superfluid. Anyway, so that's work in progress, but there is a lot of exciting things to, yeah. Good, so these are the Fermi-Hubbard quantum simulation, very much related to material science and so on, and models that are motivated by material science, Fermi-Hubbard models, and so on. Of course, you also wonder about quantum computer, right? So what is a quantum computer? Can we use this to build a quantum computer? Well, a lot of the things that I said today give you a little bit of intuition why people think quantum computers can be, or in what ways quantum computers can be more powerful. Right? In our case, it was the atoms that were in many places at once somehow and then interfered, and then you get one result in the end, which really relied on before you took that snapshot, the atoms were in many places at once. And the quantum computer essentially is hand-wavingly, it's doing a lot of calculations a little bit simultaneously. You don't get the results of all of them, but if you put them all together again, then you get one result which really reflects all these different paths, all these different calculations essentially. Just like how for the quantum walk, you know, just how the single particle took all these paths. In a quantum computer, you kind of take all the calculations simultaneously a little bit. They let them interfere and get the end result that reflects that structure and that nature. As you know, it's challenging. There are different platforms, right? Superconducting qubits and ion traps are some of the most traditional ones, or also with optics. Could we use cold atoms? Yes. In fact, that is a very interesting platform, and we have recently developed cold atoms with Rydberg interactions. The idea is that we start with an array of atoms. So these are experimental pictures here where we can program arbitrary arrays, and then we can program interactions between them using Rydberg interactions. So Rydberg is really highly excited electronic states, and so we can engineer interactions between these particles using Rydberg. I don't have time to go into details here, but just flashing a few things. What's nice is that we can assemble these quantum registers, these perfect quantum registers, and then use, let me go forward a bit, right? And then we can essentially program, by programming patterns or by programming Rydberg interactions in different ways, we can realize all kind of different models. And so recently, we have realized, so I should mention this is a collaboration between Misha Lukin's group and our group and Vladan Vuletic's group, and this is led by Misha Lukin. For example, we have seen evidence for spin liquid states, but then it's also possible to do experiments that do not, or to do quantum simulations that are not linked to physics problem, but more to other kind of problems like optimization problems. So we did some maximum Hen and Z problems there. But recently we have also shown how we can shuffle atoms around and really have a very scalable platform to do a more gate-based quantum computation based on that platform. There's also a company we formed to make this available on the cloud, essentially for everyone to play with. Good, so you saw how ultracold atoms give us these amazing quantum systems to play with, and how we can build really complex matter with that, and the quantum simulation. And so with that, I would like to thank you very much for your attention, and I would like to thank the whole team and the funding agencies for all the work. And thank you very much.